In this video, I go over how to estimate a quantity by taking small sums of that quantity. As an example of estimation by summation, one day a long time ago when my daughter was young, I asked her, here is a glass that is partially filled with water. Can you tell me how much water is in here? Now, you can't use a measuring cup though to do so. So she thought about it, and her first response was a logical one, which is just take another glass and fill it about the same amount. But then I said, but if you do so, that only thing you've then accomplished is that you've said that the amount of water in my glass is half full, just like your glass is half full. That's a lot of variation in our answers. Can you be more precise? So she looked around and said, I'll take a dropper. I'll just constantly take out liquid out of the cup, a dropper full, and then I'll have that many droppers. This is exactly the idea behind estimation by summation. You simply measure small parts of the thing that you want to measure, and then you add them all up. To enable us to visualize the overall process, let's suppose our desire is to find the area between a positive function, the x-axis, and two vertical boundaries, x equals a and x equals b, where here I'm assuming that a is actually less than b. This is one of the primary questions behind calculus. It's very different from the tangent line problem. But the area finding problem and the slope of the tangent line problem, they both use an approximation model, and then they use a limit in order to go find the actual answer, or to define what the answer should be. For example, consider the area bounded by the function f of x equals x plus 4 divided by 4, the x-axis, and the lines x equals 0 and x equals 4. You should recognize that is a trapezoid, and we could easily find the area of that trapezoid using the formula we already know. But instead, let's approximate it. Now to do so, I will fill or superimpose on top of this region a bunch of rectangles. I'll find the area of those rectangles and then add them together. The sum of the areas of the rectangles would then be an approximation to the area of this trapezoid. Now, in order to go design these rectangles, we need a process to follow so we can make it be somewhat systematic so we can repeat it. So the first thing we'll do is we'll take the interval of the x-axis over which the region is above. We'll break it into equal length subintervals, numbered left to right. So we'll have a first, a second, a third, and so on, number of intervals. For every one of these new subintervals, we will create a rectangle above it. The width will equal the length of the subinterval. The height will equal a function value, where we find the function value by evaluating the function at an x value inside that subinterval. And to make things easy, we'll just always choose in every subinterval the rightmost x value for c. This new estimate will then be the sum of the areas of these rectangles. For example, I want an upper estimate on the area, and I will use two rectangles to do so. So I will take the interval from 0 to 4. That length is 4 minus 0. I'll then divide by 2 to get the subinterval length being 2. That will then tell me what x values will then begin and end my subintervals. If I start at 0, the first subinterval ends at 2. If I start at 2, the subinterval then ends at 4. Notice I have two subintervals now of equal length. In every single subinterval, I will pick the rightmost x value to evaluate the function to get a height. By doing so, you get those heights. So in the first subinterval, I use the height above 2. That builds in that rectangle. And then over the subinterval from 2 to 4, I use the rightmost x value to get a y value, and that defines another rectangle. The area of those two rectangles would then be an estimation on the area inside the trapezoid. And it's clearly more than the area of the trapezoid. This is often called an upper sum. I'm guaranteeing that over every single subinterval, I am always picking the largest such function value. Because of that, for every subinterval, the rectangle will always be above the graph. So the area of every rectangle over a subinterval is always an overestimate to the actual area we're trying to compute. So in this one particular case, I could say then the area, which is the sum of two of these rectangles' areas, is found by taking a function value f of 2 times the width, 2, plus a function value f of 4 times the width, 2, and that is 7. So the area of this trapezoid is about 7, and it's certainly less than that. But there's no reason to use only 2 rectangles. Let's use some more. This time I'll try it with 6. So it's the same process. I'll take the subinterval. I'll take the interval from 0 to 4, and I'll break it into 6 equal lengths. To do so, the length of the interval is 4 minus 0, and then I divide by the 6 to get the length of each subinterval. This allows me then to find out the beginning and end of each of these subintervals. So if I start at 0, the subinterval ends at 2/3. If I start at 2/3, the subinterval ends at 4/3. If I start at 4/3, the subinterval ends at 6/3, and so on until I get to 4. That gives me all these x values. For each of these intervals that I've just created, I'm going to pick the rightmost x value because I'm guaranteed, looking at my function, that will give me the largest possible y value over that subinterval. That way, when I create my rectangle, the height will be larger than every other y value in that subinterval, guaranteeing the rectangle is an overestimate in terms of area for the area that I'm interested in for that portion of the process. So, by doing so, in every single subinterval, as I said, I picked the rightmost x value. That gave me a function height. That gave me a rectangle that would be more than the area that I needed to compute for that portion of the interval. And I just add up all those areas. If I do so, the area then is about the sum of 6 such areas of rectangles, and that would be the function evaluated at 2/3 times the width 2/3. It'd be the function evaluated at 4/3 times 2/3. Plus, you do it 6 times, the very last one would then be the function evaluated at 4 times 2/3. If you add that up, it's about 6 point with a repeated 3. Then that area, 6.3 repeated, that is more than the area that we're actually supposed to compute. It's an overestimate. Now, I'm giving a little bit of freedom. You don't have to go in every subinterval pick the rightmost x value. You can pick really whatever you like. If you want to be systematic, you could say I will always pick the leftmost x value. In this case, that would create what's called a lower sum, because in every subinterval, since the function is increasing, if I always pick the smallest such x value, that would give me the smallest such function value. And when I create my rectangles will then be inside the region. So each area of each rectangle would be an underestimate to what I want. You could instead go and pick, in every subinterval, pick the middle x value. That's often called the midpoint rule. So there's many ways to do it. So in general, though, the area of the sum of all of these rectangles is done by the same formula. You take a function value, evaluate at some x value in the interval, times the width, change of x, plus, for the next rectangle, you evaluate the function at some x value in that interval, and then you multiply by a change of x, the width. You just do that however many times that you have rectangles. I want to show to you in general what it kind of looks like. Now, there's more uses than just computing an area. Suppose that you have the velocity of a projectile is fires straight into the air and is given by this formula in meters per second. I'd like to know then, can I use a summation process to determine the distance traveled by the projectile over the first 3 seconds? Now, I'm not going to get the exact answer. I'm just going to approximate it. To do so, I'm going to think of the total distance as a small sum of smaller distances, and I'll find each small distance traveled by taking the speed and multiplying by how much time has elapsed. Now, the speed is changing, assuming the velocity is always positive in this case. If so, since the velocity is a decreasing function, if I used the later time in any subinterval, I would use the slowest the object was moving over that time period. If I then multiply that speed by the time that has passed, I would get a distance, but it would be an underestimate on the actual distance traveled over that time. On the other hand, if I use the earliest time value, that would be the leftmost time value when we do this in a picture, that would correspond to the greatest such speed over that time interval, and therefore, if I multiply that speed by the time that has elapsed, that would give me an overestimate on the actual amount of distance traveled by the particle over that small bit of time. So please note that the projectile's velocity was greater than 0 that whole time. That means that the velocity of the object is the same as the speed of the object. I'm going to partition this time interval from 0 to 3 into a certain number of subintervals. Each one will be called the first, second, third, or fourth, or the kth if we want to talk about it generally. And in every such subinterval, I will go and pick a certain time. I'll call it t sub k in that interval. Now in my case, I'm going to use only 3 subintervals. And I remember that the distance traveled over that one sub-time interval would then be equal to the estimate of my speed during that subinterval multiplied by how much time has elapsed. So the distance should then be equal to the approximate speed in the first subinterval multiplied to how much time has elapsed in that first subinterval, plus the estimate of the speed in the second subinterval times how much time has elapsed in that second subinterval, and so on, all the way to the very last subinterval. Since I'm only using 3 of these, I will use these 3 time intervals. Notice that the length of each subinterval is 1. I'm allowing 1 second to pass. And t1 is a time in the first subinterval, t2 is a time in the second subinterval, and so on. By using that, and the formula I gave you for d, the distance should then be equal to the velocity at some time. I will pick the lower time because I want an upper estimate on the distance traveled. I know my velocity was always decreasing. So in the interval from 0 to 1, the velocity at 1, the speed at 1, is certainly a lot slower than the speed at 0. So I'll pick the largest speed. That would be the velocity at 0. So I have the velocity at 0, my estimate of speed in the first subinterval, times the amount of time that has passed, plus then I have my estimate of speed in the second subinterval, and again I'll pick the lowest time interval because I want the largest such possible speed, and I'm picking the earliest time because the velocity was always decreasing and it's always positive, so the greatest speed is at the earliest moment. So that would be the velocity at 1, the speed estimate in the second subinterval, and then I multiply it by how much time has elapsed. And I do the same thing for the very last subinterval. It would be the speed at 2 seconds, my estimate of speed for the whole time interval from 2 to 3 seconds, times how much time has elapsed. If I evaluate the function and multiply all these things by 1, you get 240.6, and that will then be an overestimate on how far this particle travels over this time period. It's less than that amount. Let's continue with that example of our particle that has been shot into the air with a given velocity, and let's try to get a lower estimate on the distance traveled. I'll do so by taking the interval from 0 to 3 seconds and breaking it into 6 equal subintervals of length of, I say, a half a second has elapsed. If you want to see it, this would then represent the overall time interval from 0 to 3. I have broken up into 6 subintervals, and at each subinterval I'm going to be using the rightmost time value, because since the velocity was decreasing the entire time, by picking the greatest such time value in any subinterval, I'm guaranteed to get the least speed estimate for that time interval. So here I am evaluating the distance, which is just the velocity evaluated at some time to get my estimate speed times the time that has elapsed plus, and I do that 6 times total. Now in the first subinterval, that first subinterval would go from 0 to a half because the subinterval is of length a half. I'll pick the largest such time value to get the least amount of speed. So that's why I evaluate the velocity at a half. I multiply that velocity at a half by half because that's the amount of time that's elapsed from 0 to a half. I do that then for every single subinterval. When you do so, you get this distance, 398.55 meters. So we know then the particle travels between those two amounts. But something else is interesting here. What I'll do is this time I will look at different subintervals, and I will get a lower estimate on the distance traveled by always picking right endpoints in every subinterval, and I will get an upper estimate by always picking the left endpoint of any subinterval. Then I'll know that the actual distance will be between these two values. And then I'll do the exact same process, but I'll just increase the number of subintervals. I won't actually write down all the computations because I've already shown you how to do at least 2 of them, but I'll give you the results. So if you use only 3 subintervals, that means the subintervals lengths are all only 1 second long. You get a lower estimate of 391.2 meters and an upper estimate of 420.6. I did the same thing with 6 subintervals. If you have 6 subintervals, there are now 6 subintervals of all equal length. Each one only represents a half a second that has elapsed. By always picking the rightmost time value, that would give me a lower estimate, which is 398.55, as I have already done on this particular slide. But the upper estimate, by always picking the least time value in any subinterval, it would give me 413.25. The important thing is notice that by going from 3 subintervals to 6 subintervals, these 2 numbers, the lower and the upper, are getting closer together. And as you go and use more and more subintervals, they become closer and closer, so that we suspect that in the limit that these 2 numbers are the same thing in the end. And that would be the actual distance traveled. So if you look at the very last instance, if I did 48 subintervals, every single subinterval would only correspond to a 16th of a second of time elapsing. The lower estimate is 404.98, while the upper estimate is 406.82, and that'd be meters. I would bet then that the actual answer is somewhere smack in between them. In summary, in order to compute some kind of quantity, we'll imagine the quantity as the sum of some form, where we have a function evaluated a number times the change of x plus a function value times the change of x, and so on, where f is just some kind of function defined on an interval, broken into subintervals of equal length the change of x. We'll just hope that as we let n grow without bound, as we break the subinterval into more and more and more pieces, so that each of these products becomes incredibly small, but we're adding up many of them, that sum approaches a value, and it doesn't matter how we make our choices of the x values in these different subintervals. To automate this process, we're going to need notation. That's called summation notation, and it's the next video. And that gives you a basic introduction to estimation by summation and gives you a justification for why you want to learn summation notation.